Chapter 14, Lesson 3. In this lesson we'll talk about how temperature affects the rate. And in general, the relationship is always the same. As temperature increases, so does the rate. But the increase is usually exponential. So the higher the temperature, the rate really kicks up very quickly. And the reason for this usually is explained in terms of K. Remember, the K is the rate constant, being temperature dependent. So if you recall, our rate laws that we developed from last time had the form of rate equals your constant times your concentration. So as K goes up, rate goes up, essentially. Now, the details of how temperature affects rate will be explained using the collision model. And earlier on, we stated that in order for a reaction to proceed, to go forward, the molecules literally have to collide with one another. They have to find one another and collide. And two things must be true. The molecules must collide with the correct orientation and with enough energy. So an increase in temperature essentially allows the molecules to hit each other more often, and that allows them to find the correct orientation, so it helps there. And then, but more importantly, the energy is higher with every collision, which allows the reaction to proceed. And here's a little example, or a little picture of that process. And the more important factor is that second factor, that idea of enough energy. And this is dealt with something called activation energy. Every reaction, in order to proceed forward, must surmount or must overcome a certain energy barrier. And this can be modeled with a picture like this, a little caption of a golfer which needs to take the golf ball and swing it over this hill. And this hill, the higher the hill, the more energy must be placed into the, must be transferred to the golf ball. So the activation energy is what holds the key to explaining how increasing in temperature allows us to increase the reaction rate. And this is usually signified as E sub A, or the energy of activation. And we can actually draw a similar curve for a reaction. This is called the reaction coordinate diagram. What happens, you have your reactants on the left side. You begin with your reactants and you end up with your products. And the energy that must be overcome in order for the reactants to become products is here, represented as the activation energy. These are pretty common. Many reactions can be represented using this energy coordinate diagram. So the details of the coordinate diagram, it shows the beginning energy and the ending energy, and we can then calculate the change in energy, in this case the change in enthalpy, just the heat portion. Remember, this is enthalpy, or heat. The high point is called the transition state. And usually in the transition state, this is kind of like the middle of a reaction, you have what's called an activated complex. This is essentially a substance that gets formed in the intermediate steps of the reaction. Eventually it gets, it further breaks down into products. But we can actually analyze this activated complex. Very often we can isolate it or study it at least. And then the activation energy barrier is where you can say the activated complex sits. Now we're going to take a look at something called the Maxwell-Boltzmann distribution, and this is essentially the details, explains the details of how increasing temperature allows the reaction rate to increase. These are kind of the details of the phenomenon. So the Maxwell-Boltzmann distributions treat the energy of a collection of molecules using one of these curves, and these are what are called distribution curves, and usually used in statistics anytime you're dealing with a very large population size. And anytime we have a collection of chemicals, even if it's a small amount, you know, a tenth of a mole, we have literally billions and billions of molecules. So we have to think of them in terms of an average, or this distribution curve in terms of a population. So what happens is, in a distribution curve, most of the molecules have an average energy, an average kinetic energy. A few molecules have a low kinetic energy, and a few molecules have a high kinetic energy, but most of them fit technically into this middle portion, to the average. Now, anytime you increase the temperature, what you do is you lower the curve and you extend it to the right, and this is what this curve is represented by. So what happens, the curve broadens, and then the number of molecules that go to the high and the low essentially increase. Now, if we say that the activation energy is a minimum energy amount, say this point right here, molecules must have at least this much energy in order to go to product. Well, what happens in the higher temperature, the curve broadened, and so now you have a bigger amount of molecules that are able to come over that curve, and therefore the reaction rate increases. So at any temperature there is a wider distribution of kinetic energies, so more molecules have this higher necessary kinetic energy to become products. And this I think says a little more, carries or talks about a little more in detail. So really same thing that we said, the curve broadens, and if you were to increase the temperature once more, you'll broaden the curve even more, and you'll have a higher amount of particles coming over that barrier. And this is I think just the same thing we just talked about, the fraction of molecules that can scale that barrier increases, that energy barrier. And finally, the rate increases. Okay, so why don't we do a little example with 3 of these activation energies, or coordinate diagrams. Here it says, consider these 3 energy profiles. Which reactions are endothermic and which are exothermic, and then rank the reactions from slowest to fastest. So if you recall, endothermic means there is an absorption of energy. The system absorbs energy. And exothermic means the system releases energy. So if we analyze the first reaction here, we begin at a higher energy and end up at a lower energy. So overall, the system releases energy because it ended up at a lower state than it began. Same thing with the second one. We began at a higher and ended up at a lower. So both of these are actually exothermic. Both of them are exothermic. The third one begins at a lower state and ends at a higher state. So energy is actually absorbed. The products have more energy than the reactants, so they must have absorbed that energy. So this is your endothermic process. Now question 2, rank the reactions from slowest to fastest. It turns out it depends on the activation energy. So really, the lowest activation energy would be, we can actually analyze it. We're given some numbers here. So we see that the activation energy, this is the energy of activation, is 15 kilojoules per mole in this first one, 25 in the second one, and not quite 20, but that's 20 minus this amount here. So it turns out that this one is actually less than more than the first one, right? So this one's 20. There we are. This is 20. And so from the slowest to fastest, the slowest one would be this, then this one here, and the fastest one will be this one. So fastest and slowest. And again, the idea here is the one that took the least energy to scale will have more molecules being able to scale that barrier, increasing the rate. And then this should conclude our lesson 3 of chapter 14.